Okay, we are going to be starting the second half of this chapter, but it really ends up being like the last third or last quarter. And this is on perception. So we've talked all about sensation, so how different signals come from the environment into our body and are transduced by our eyes, ears, nose, skin, mouth. And then now we're going to be talking about how the brain actually makes sense of this all. This first image here, we have a lot of really cool illusions in this section, a lot of really cool GIFs, movies, and pictures that are just going to kind of mess with your mind a little bit. So this first one, if you take a look at it, this is actually a still image, although it looks like the circles are slowly rotating. They're actually static images. They're not actually moving at all. But the illusion here is that it actually looks like they're kind of twisting. If you focus on one, they kind of stop twisting, but if you're not paying attention directly, it looks like it's spinning. It's a really cool one. So we're going to be talking about top-down and bottom-up processing first. Then we're going to go through the Gestalt principles, depth principles, perceptual constancies, illusions, and ESP, or extrasensory perception. So if you look at the middle shape in this picture here, this blue box, if you're seeing a B or you're seeing a 13, it probably depends on which row those shapes are in. So if you look just the top row, you're going to see the letters A, B, and C. If you look at the bottom, you're going to see 12, 13, and 14. But these middle figures, the B or 13, these are ambiguous, and it has to do with the context that they're surrounded by, whether you would interpret this to be a B or a 13. And we're going to be kind of talking about this shape and this figure quite a bit in the next few slides. So, first we're talking about top-down processing. This is when we use context and pre-existing knowledge to rapidly organize features into a more meaningful whole. So you know what numbers and letters are, and you know the numbers and letters that are needed to complete the sequence. So if you're seeing a sequence that it's A, an ambiguous figure, and C, that ambiguous figure you're going to assume is B because you know that the alphabet goes A, B, C. Same thing with the numbers in the bottom. So you're using context. You're using your knowledge about letters and sequence to complete that, or to figure out what that image is. So even though it's the same stimulus in both rows, you can interpret it differently depending on the context. And that's top-down processing. You're using these bigger, higher order things, like this knowledge-based approach to figuring these things out. On the other hand, we have bottom-up processing. With bottom-up processing, we start with raw materials. So we're going to look at the shapes, the small sensory units, the basic features, and then build upwards to a more complete version of that perception. So if you saw that B or 13 stimulus by itself, you would recognize that it's ambiguous. You would look at the shape of it. You would see the single line and then the two curves, and that they're not connected, the line and the two curves. You're going to look at the basic shapes, and then from there, you're going to build your general perception of whether it's a B or 13. Again, so top down uses context and knowledge and higher order thinking, and then bottom up is using basic perceptual features. It has nothing to do with looking from the top to the bottom or bottom up. It has to do with how you organize the information, whether you're using broader clues or really basic features. So here's another example of this. If you've ever been to Animal Kingdom, you probably know that there's a giant tree in the middle called the Tree of Life. Imagine you're a small child and you're in a stroller. Your parents have brought you to Animal Kingdom. And as you're coming up to Animal Kingdom, you're being pushed in the stroller and you see this giant tree. If you're using your top-down processing, what you're doing is you're looking at the holistic picture. You're seeing this whole tree. And it's not really until you get closer that you see that the trunk and the bark is all made up of a bunch of different animals. So you've gone from the broad picture to the smaller details. But imagine you're the same child, you've been asleep all morning, you hadn't seen the tree yet, and you wake up and you're sitting right next to the tree, and all you see is this big brown surface, and it's a bunch of different animals. And you're like, oh wow, look at animals. And then as you slowly maybe back away from this close-up image, you're gonna see the holistic tree. So you're going from details to the broader context. Again, this has nothing to do with looking up or down. I want you to erase that from your mind. You're using the details to understand the holistic picture, and then top down is using the holistic picture to then see the details. Have you ever seen one of these mosaic pictures before? This is kind of the same idea. So on the left, you see Mona Lisa, but that she's made up of a whole bunch of different smaller images, and these would be the perceptual units or features. So depending on how close you are to the image, you may see the details first, or you may see the holistic picture first. Now we're going to be talking about Gestalt principles. So if you remember back to chapter 1, we mentioned Gestalt early on. So Gestalt is German for the word whole. And what it says is that we have a number of built-in tendencies that help us organize information that comes to us in certain ways. We tend to simplify problems to help recognize objects, movement, and patterns. And if you remember, so whole, the Gestalt, it means like the whole is greater than the sum of its parts. So there can be a lot of little things that we're noticing, but the holistic picture is more important overall. So according to Gestalt principles, if you look at this image here on the right, you're going to see a face, and unless you zoom in, then you see a bunch of men, horses, tree. You see those details later on. Okay. One of the other Gestalt so we're going to be going through the Gestalt principles. The first one is called figure ground. When we perceive a stimulus, we typically visually pull the figure part forward, and then we push the background to the back, and then we focus more on the image to the front. So if you look on the image on the right, you see a vase, and it's kind of a maybe asymmetrical vase. But if you can kind of flip your Gestalt figure ground principle around and you focus on the background, you'll see that two faces show up in profile along the edges of that vase. And it's not just two of the same faces, it's actually two different people. On the left, we have Prince Albert, and on the right, we have Queen Elizabeth. And this was given to them as a wedding gift. So you actually have their profiles from when they were married on either side. So you have left is Albert, right is Queen Elizabeth. And so it's kind of a neat image. You may have only seen the vase at first, but now that you've kind of learn to adjust your normal Gestalt principle of figure ground, you can actually see the newer image. All right, according to Gestalt principles, we tend to group things by similarity and by proximity. So if you look on the left, we have these dots, and we are mentally grouping these dots as vertical lines in this figure and in horizontal lines in this figure because of their color. So we're grouping this blue column separate from this yellow column. We could mentally group these horizontally, but it's more awkward for our brain because the similarity goes with the vertical lines. So same thing here. We could look at these vertically on this bottom one, but we actually group them horizontally here. Same thing happens with their distance. We're more likely to group these as columns and these as rows because they're slightly closer to one another. Now we could look at these things as horizontal rows or as vertical columns here, but we're more likely to do the opposite. We're more likely to group things that are closer to one another as part of the same group. Another Gestalt principle is continuity. We have a tendency towards simplicity and continuity. So if we look at this image, we probably believe that it's actually just one long piece of rope, let's say, and not multiple pieces. So take a second and kind of follow these things around. Have you noticed that there's actually two pieces, two actually separate structures from one another? So if we start here, we're going to go around. So we're going to go here, go up, go down here, come around, down here. Oh, and we're back here. But we never touched these loops over here. So let's start over here. Go down here. This links up here, down here, and we're back over here. So there's actually two separate pieces in this figure, even though our brains would like to simplify it and make it one continuous piece. So this is the principle of continuity. Another principle is closure. So we have a tendency to complete a figure. So if you look at the The image here, you probably see a star, even though there are no lines. It's just triangles and little Pac-Men. So there is no line across here, but our brain fills it in. Same thing happens with the World Wildlife Federation panda. There's no line here to connect his ear or his eyes to his nose. They're all kind of just floating in space. But with closure and continuity, we put those things together and we fill in those lines in our heads. Another Gestalt principle is that of common region. This is similar to proximity and similarity. So we have a tendency for items in a region to be seen as a group. So we see a group here of stars, a group here of stars and circles, and a group here of circles. Now, if we use the principle of similarity, we would be grouping all the stars together and we'd be grouping all the circles together. We wouldn't be grouping them three separately, but because we have these backgrounds, we've now designated common regions and we've separated them into three groups instead of just two groups. We could also use the principle of proximity and group maybe these lines horizontally or maybe just vertical groups, but again, we've broken it into three because we have a common region with the background colors. Depth perception. So even though this is a 2D image, you can see that there's depth in it. This is from Avatar, the floating islands. So we use monocular and binocular clues to allow us to perceive depth. So monocular means one eye and binocular means two eyes, hence monocle or binoculars. And so even though it's a 2D image, we see things that are layered on top of one another, so we would assume depth. This happens to us in day-to-day life. So if you put your hand, say, in front of your computer screen, you know that your hand is in front. You can see that depth because of your binocular clues. And we're going to go through that a little bit more later on. So some monocular clues are linear perspective and relative size. So on the left, we have linear perspective. That's if you look at like a straight road, and it goes off into the horizon, it actually gets smaller as it moves away from us. We don't really necessarily notice that very often, but if you've ever taken an art class, you know about keeping linear perspective consistent. On the right, we have what's called relative size. It looks like we have like some giant player and then like some little teeny man playing baseball. They're actually the same man. It's just an image that was taken for a baseball card and like old school photoshopped it together, and it just makes it this really awkward image where it looks like it's two different people of very extremely different sizes, but it's actually the same man. So the relative size looks different, even though we have some foreground and background clues here with their legs and the way that they cross over. It still doesn't look right to us because of how much larger this man is, especially because they look like they're on the same surface. It's a very strange image. Monocular clues are also interposition or overlapping. So we know this isn't just like one large blob of horse heads and legs. We see that it's actually a bunch of individual horses that are overlapped on top of each other, and like this horse is closest to the foreground, and maybe this one or this one's in the background. Same thing with the mountains. We see that this is the mountain in the foreground, and some of these are further in the back. So these are the monocular clues of interposition or overlapping. We also have clues of texture gradient and light and shadow. So here we have light and shadow. So these are, again, just 2D images. And because of the gradient that has been given to these objects, we see typically these as kind of popping forward or being convex, and these ones going inward, which is concave. Now, if you stare at it for a few minutes, you might actually be able to get them to switch, where this will be concave or going away from you, and this will be convex or kind of popping forward. You can kind of manipulate that with your mind a little bit. We also have texture gradient here, so this is just like a field of flowers. We see some interlapping or interposition, but as the texture kind of changes and becomes smaller over time, we know that this is still flowers. We know that the texture, they haven't gotten larger or smaller as they come closer or further away from us. It's just that texture gradient that we begin to understand as part of those monocular clues. Some other ones, we have aerial perspective. So if you're seeing a city from a helicopter or an airplane, you actually can see all the buildings at an angle, and you understand kind of your relative position and their relative position to one another, that they're not just flat images. We also have what's called motion parallax. So if you've ever been in a car or on a train, you're moving forward and the ground that's kind of close to you, so trees and objects, other businesses, they seem to be moving past you, going backwards. But then at the same time, things that are really far away, like the sun or clouds or the moon, they seem to move with you. As a little kid, you may have like noticed in the car driving with your parents, like, oh wow, the moon is following us. It's actually not, of course, the moon isn't following you, but it's just so far away that relatively it looks like it's staying in a similar position and kind of moving along with you. And that's part of that motion parallax. Even though everything is moving past you, things that are super far away look like they're moving with you. Now, binocular clues are also known as convergence. So when we're looking at objects in our environment, we're actually using both of our eyes unless we have some sort of eye condition where we're not using our eyes together, and we focus on objects that are either close to us or far away from us a little bit differently. And our eyes have to turn in to focus on really close objects. So if you look at the tip of your nose, you're going to cross your eyes and you're going to look funny, like you see in the picture here. And you're converging your eyes to focus on that near spot. Now, I'm going to ruin your day, but did you know that all the time you can always see your nose in your peripheral vision? No matter where you are, you can see your nose, but because, once again, our brain is amazing, because it's unchanging and it's not necessary for our understanding of what's going on around us, we typically, our brain just like tune that out and kind of gloss over it. We're not noticing it anymore. And so it's actually a pretty neat phenomenon that, we normally don't even notice it until we look down and actually stare at it. But have you ever gotten something on your nose, like some, like maybe some frosting from a cake, or you get a zit on your nose and you can see it kind of all day and it kind of bothers you? That's again because the stimulus has changed. Your brain is beginning to notice it then. So binocular clues are based off of what's called retinal disparity. So that's the difference in apparent position of an object as seen by the left and right retinas. So I want you to find something off in the distance, like a spot or something that you can easily kind of single in on one spot. So you put your pointer finger on that spot with both eyes open. Now close your left eye and close your right eye. And you're going to see, depending on how close that object is, that your finger's going to jump on one of your eyes. That means one of your eyes is actually dominant. The one that, the finger doesn't move a whole lot, that's your dominant eye. And your other eye is your recessive eye. And then your brain puts these two images together to create this 3D perception. And now you have a large disparity if the object is close and a smaller disparity for distant objects. So find something that's kind of close to you and do this trick, and then do it with something really far away, and you're going to see the jump change a little bit between the two. Okay, so these are some really cool images, and I'm just going to throw a bunch of really, really cool images your way. All right, so this is what they call a magic eye or a stereogram image. These were huge in the 90s. Everyone had these books and posters, and there were bands that had album art that was done with this. So what you do is you have to essentially look through the object. It's kind of tricky to do. What I recommend is you hold it close to your face and you slowly pull out with kind of looking through your computer screen. This image actually has a ground with two palm trees that are kind of curving in towards each other and in towards you as the viewer. A 3D image will pop out if you do it right, and once you get it, it's pretty easy to hold the image and kind of look around it. If you can't see this one, I recommend you search for magic eye photos, and you can go through thousands of these on Google Images or wherever else you're searching, and it's actually really, really, really cool. It might take you 10 minutes. It might take you the whole weekend to figure out how to do this with your eyes, but it's a really neat trick. And I have some magic eye books in my classroom that I'd like you to check out. I also, in the playlist, I have a music video, and sometimes actually that works better for people because it's longer, but it's a stereogram magic eye. The song is by Young Rivals, and I forget what it's called, but it's in the playlist. Check that out. There's also another 3D image version. It's a little bit different than the magic eye, so check that one out. It's a spiral with some stuff moving around it, so check those out. I think you're going to find them really interesting. All right, so perceptual constancies. So we have the tendency to perceive objects as the same even when their physical characteristics change. And this works for size, shape, brightness, and color. So here we look at, if we look at what looks like the dark blue shapes here and the yellow shapes here, if we pull these down, they're actually the exact same color, but because the background, like essentially the context lighting has changed, we perceive them differently. And this is actually what's going on with that gold and white dress versus the black and blue dress, or the shoe that goes from mint to white, or pink, I think it's, yeah, mint or pink. That just, that has to do with the coloring around it. That's why we kind of get mixed up with those things. So here's another example. If you look at square A and you look at square B, you probably are noticing that there are two different shades of gray. But what if I told you that they're the exact same shade of gray? You don't believe me, right? What about that? So this is the exact same image. All I did was paste it onto the next slide, and then I used the little dropper feature in PowerPoint to create these little bars. These are the exact same. So if you actually go back here, maybe put your fingers on either side of those letters, and you can see that they're actually the same. Pretty cool. Because of the relative shading that we actually think that they're different. There's also a video about color that you should check out. It's in the playlist. Just watch it. It's pretty cool. It talks about some of these phenomena as well. All right, so constancies. So we have size constancies. This is when we perceive objects as remaining the same size, even when their images on our retina continually grow or shrink. All right, so if you hold your phone near your face, it has one size. If you hold it out the end of your arm, it looks a little bit smaller. If you put it on the other side of the room, it's going to look even smaller. But your phone has not grown or shrunk in size. It's just the size of it on your retina, because it's closer to you or further away from you, has changed. But we perceive it as being the same size. That's a size constancy. The same thing happens with shape. When we perceive an object, the size constancy is when we perceive an object as retaining its same shape, even when you view it from different angles. Its shape can continuously be changing its image on your retina. So when you move a book, the shape projected on your retina may change from rectangular to trapezoidal, but your perception of the book doesn't change. So granted, if you grab your phone and you hold it square in front of you, and then you turn it so you're looking more at the phone charger on the bottom, you perceive that, the size and shape of your phone has not changed. But if you actually pay attention, now the shape of your phone is actually trapezoidal on your retina. It's actually not the same shape, because the top of it is further away from you, the bottom of it is closer. So the bottom's going to be perceived to be a little bit larger. Same thing happens with color. If you walk into your dimly lit closet and you see like a bright red shirt, you're still going to perceive it as bright red, even though if you really pay attention, because the lights are out, it's really dull and grayish, we perceive it to have the same color. So you can do brightness constancy. That's the brightness of an object has remained the same. And the color constancy is when we perceive the colors as being stable, despite the differences in lighting. You can do this right now if you're, in your bedroom. Look at a brightly colored object, maybe like a highlighter or something, bright red or bright orange. Turn off the light; it's going to look like a dimmer color. And then you turn the light back on, and you perceive it as the same color, but the actual shading has changed on your eye. But we perceive it as being constant because we are smart human beings. This is actually a really funny Onion article that I saw, and I had to share it. It says, "Study: people far away from you are not actually smaller." And it says on the bottom, researchers say that, contrary to prior assertions, the subject above stands at equal height at left and at right and does not grow smaller as he walks away from the camera. So they're actually just making fun of perceptual constancies, especially size constancy. And so it's just a funny image, and I'm always happy when popular media kind of picks up on these silly things and I can use them in my class. Here's some more optical illusions. So we have the Mueller-Lyer illusion on the left. So in this one, this little line here, how does that look relative to this vertical line here? Do they look the same length? Does one look longer than the other? Which one's shorter? This one probably looks a little bit longer, and this one probably looks a little bit shorter. But actually, they're the exact same length. Again, if you cover up using your hand or maybe a piece of paper, you can actually see that they're the exact same. So hold over the little bars here. And it's because this one is viewed as being closer, this one's being further away, that we actually view them as being different lengths. Same with the Ponzo illusion here. These two yellow lines look to be very different in size, this one being smaller and this one being larger. But again, if you hold up something on either side, just to the edges, you can see that they're the exact same length, which is really cool. So here's the lines here for the Muller-Lyer illusion. You can do the same thing easily with the Ponzo. So illusions are a perceptual experience in which you perceive an image as being so strangely distorted that in reality it cannot or does not exist. An illusion is created by manipulating perceptual clues so that cues so that your brain can no longer correctly interpret space, size, and depth clues. So I'm going to blow your mind again in the next couple of slides. So first we have the Ames room. The person on the right looks huge compared to the person on the left, but they are both normal, average-sized human beings. What's going on here is actually the structure of the room itself has changed and makes it appear that they're different sizes. So the guy on the right is actually much closer, and the floor has sloped up and the roof has sloped down. The guy on the left, he's really far back, and he is in a part of the floor that is sloped down, and the ceiling has sloped up. Now, we perceive the floor and the ceiling as being pretty much square to one another, but it's because of the viewpoint of this room. So here's how it actually looks. You have to look through the view hole right there in the center in order to get the illusion. Otherwise, it's not going to work. I'm going to put a video in. There's a video in the playlist that will kind of illustrate this for you, and you'll be able to see how this works with Phil Zimbardo, of all people, walking back and forth between the two different ends of the room. So please check that out, and it's pretty nifty. What do you see in this image? I'm going to give you a second here. All right. Do you see anything in this? All right. So you can pause the video. I'm going to spoil this in 3, 2, 1. It's a cow. So if you maybe see it now, maybe you don't. Here is the first ear. Here's the second ear. He's facing forward looking at you. There's one eye. There's the other. You have the bridge of the nose or snout of the cow. Here's like the side of his face. Kind of, there's another one here, and like his back is going this way. This one's kind of tricky. There's another one of a Dalmatian out there that you can check out online. But there you go. What do you see here? Brutus, stop it. Dog squeaking back there. All right, so we have this really cool patterned image, and you're probably seeing it slowly rotate with the ball. Like the ball looks like it's kind of rotating around the center of like a tube structure. Now, it's a still image. It's not actually moving at all. This is not a GIF or a video. This is just a static image. You can find this on Google Images. Our brain is actually tricking it into thinking that it's moving. Now, I've seen things on social media where it's like, oh, the speed of the ball represents how stressed out you are, and whether it's going to the left or to the right has to do with, you know, optimism and pessimism and whatever. That's all crap. Everyone perceives it as moving. It's just we have a little bit slight variations. It's nothing to do with how stressed you are. So don't take your, you know, psychological evaluations from illusions on Facebook or Snapchat. All right, here's another fun one. So these two objects, the blue and the yellow, they're moving in tandem with one another. When they're on the striped background, it looks like they're kind of stepping with one another. So like, looks like the blue's kind of just ahead of the yellow, and they're kind of like taking steps with one another, kind of jolted. But then you see when it goes to the gray background that they're moving perfectly smoothly. But again, once they're on the other background, it looks like the yellow is always kind of trying to jump and catch up. So watch this go around for a little bit longer. All right. Here we go. Here's another one. So this is a GIF, and you'll see the looks like the lines going horizontally are becoming kind of tilted, and then they go back to being perfectly vertical. But actually, they're completely vertical the entire time. It just has to do with the black and white squares that make them look either kind of tilted up or tilted down. So you can watch this for another minute or so. It's pretty cool. All right. Here's another good one. This is a spinning woman. And do you see her spinning to the left or counterclockwise, or do you see her spinning to the right or clockwise? So try to figure that out first. And then if you really focus and you stare at it for long enough, you can get her to switch to the other direction. Okay, so I just got her to switch in my mind. She was going counterclockwise for me, and now I have her going clockwise. Let me see if I can switch her again. Oh, now I got her to switch again. So for me, what works best is I look at the shadow kind of near her foot, and when those two meet, I can usually get it to swap sides. This may take you some viewing, so I'll let this go for another few seconds. You can always look up Dancing Woman Illusion, and you can watch this to your heart's content online, or download the GIF and then save it forever and freak out all your friends. Have any of you gotten it to switch? Do you think I'm crazy? All right, here's another one. So this mask, you see it's like moving away from us, and then, it seems to pop forward, and then again, it goes away, and then you can see it being concave again. So you watch this, it'll go over and over again. This one's kind of freaky. There's a bunch of versions of this, different clown masks and Einstein masks and things like that, but this is just a simple one. I'm going to move on. All right, so this is a flicker illusion. So what you're going to do is you're going to focus on the flickering green dot in the middle. After about 10 seconds, you're going to see one, two, or all three of the static yellow dots that are arranged in the corner. They're going to disappear and then reappear. They happen pretty randomly as long as you care to look. So look at the flashing green dot, and then eventually the yellow ones will begin to kind of flicker in and out. So the yellow dots for me go away completely until I move my eyes. What do you guys think? Essentially what the brain is doing is it's taking away information it doesn't think is necessary. It's focusing on the movement, and anything that's static is just going to be kind of wiped away because it's unimportant to the brain. All right, I'm going to move on. There's another version of it. So if you stare at the moon, the stars will begin to kind of flicker in and out. How's this one working for you guys? It's kind of weird. All right, I'm going to move on. This is called the lilac chaser illusion, also known as a Pac-Man illusion. So all you have to do is stare at the cross, and then the lilac circle, there's going to be one that's going to turn like a bright green, and then eventually it looks like it eats up the lilac and then puts them back, and then kind of eats them back up again. So is that one working for you guys? This is one of my favorites. This one always kind of messes with my brain a little bit. Again, this has to go back to that opponent process theory. There's actually no green dot. It's just the purple, pink color fading away, and the opposing color to that in our eyes is that bright green. Here's a neat one. So keep your eyes on the cross, and then peripherally kind of glance at the faces. And you're going to see they're going to turn out and look really weird and distorted. Their eyes are going to get huge, and their eyebrows are going to be all messed up, and their nose and mouth are going to be all misshapen. But if you look back directly at their faces, they're 100% fine. Then again, you stare back at the cross, and they get all distorted again. So we'll watch it one more time. Did that one work for you guys? This one always freaks everyone out. All right, we're gonna move on. All right, so I also have this impossible motion video for you. So I'm gonna play this. Catchy music. All right. That's a pretty fun video. All right. I want to talk about this briefly before we kind of wrap up this chapter. When we talk about sensation and perception, we've talked about these things all as separate units. But in fact, most of our sensory perception actually is experienced with another sensory system. So it co-occurs with another sensory system. So we see and hear someone talking to us, we taste and smell something. Like I said, most of taste is actually smell. And so it's important for us to recognize that those things go together. And a lot of researchers have kind of forgotten about that. So we have to remind ourselves that it's a multi-sensory world. It's not unisensory in the way we experience it. Same thing happens within developmental experience. So language is learned in a multisensory fashion. So we see and hear people talking to us, and that's how we learn about language. Babies aren't listening to the radio. They're not watching TV on mute. They're seeing and hearing language together. They also see objects moving with sound, so bouncing balls, or like when they're in the car, they feel an acceleration while they're seeing the background movement change from the car. I also want you to check out this video on the McGurk effect. This is an audio-visual illusion that will kind of emphasize how when we change a visual perception, we may actually change what we hear. It kind of tricks our brains a little bit. So go ahead and check that out. I think it's a really great illusion for you guys to understand. Okay, extrasensory perception. The book kind of wraps up on this. It's a little silly at the end, but we're going to be talking about telepathy, precognition, clairvoyance, and psychokinesis. So, ESP, or extrasensory perception, is 100% fake. Repeat that with me. It is 100% fake. There is zero scientific evidence to back this up. But because it comes up in popular media a lot, we do want to cover it. So telepathy is the supposed ability to transfer one's thoughts to another and to read the thoughts of another person. This comes up in like America's Got Talent on TV quite a bit, or you'll see it on different social media. Precognition is the ability to foretell events. Clairvoyance is the ability to perceive objects or events that are out of one's sight. And psychokinesis is the ability to move objects without touching them. That's kind of like Eleven in Stranger Things. She has psychokinesis abilities, or psychokinetic abilities, I think is what you say. Again, these are 100% fake. There's been a lot of research to try to determine the claims of people who believe that they're telepathic or have clairvoyance or psychokinetic abilities. There was some really famous people like in the 70s and 80s who believed that they were telepathic. They went on these TV shows and stuff and would wow the audience with their abilities. But when they actually did this in double-blind trials, turns out they couldn't display their abilities anymore. It's amazing. There was one really famous one that went on, I believe it was Johnny Carson, and he came on prepared with all his, his cards that he was going to show and his little tricks and stuff. And then Johnny Carson was like, "No, you're going to use my materials." And the guy was like, "Oh, I'm just too weak to do it. I'm so exhausted from my travels. I won't be able to perform." And so he pretty much showed everyone on live TV that it was crap. So please take all these claims with a grain of salt. Look if there's scientific evidence before you become wowed or mystified, or you give your money to one of these people, because there is no evidence of any of this actually occurring. All right, so that is the end of chapter 4. I hope you enjoyed it. This is one of my favorite chapters. Next is chapter 5, which is on consciousness, sleep, and drugs. So we'll get into that next time.